So yeah, we don't have a meeting next week on 1 p.m., but we still have the 2 p.m. meeting. So as a quick review of your model that you might be making, the most common one is a neural network, right? Which consists of perceptrons. Each perceptron is taking in several inputs, right? Whatever your inputs to your model are, it multiplies them by a weight, adds them together, and then maybe also adds what's called a bias term, which is also another value. And so basically the output of the perceptron depends only on the weights inside of it, right? If you put in the same inputs, it will always output the same thing unless it has different weights, in which case it will output something different. So the weights decide how it makes decisions. However, generally those perceptrons are linear. So what we do is we start stacking them in what are called layers. So when we have our inputs here, they would first flow into a layer of perceptrons. So each of these circles here is its own perceptron that takes the previous input, multiplies it by a weight, adds it together, outputs a new number. That outputs a new set of numbers. Each of those new sets of numbers are passed into another set of perceptrons, another set of perceptrons, and so on. And basically each of these lines, the input is getting multiplied, then they're getting added together in the center, multiplied, added together, and that kind of repeats repeatedly until at the end you get a certain set of numbers on the output. The amount of input layers, the amount of input like numbers you have here is just how many inputs you have in your data set. So let's say you have, I don't know, you're predicting temperature, right? That was the example I used. If your inputs are humidity, temperature, air pressure, wind speed, that's 4 inputs. So you have 4 places for the numbers to go. Pretty self-explanatory. Output layer, it could be a different number depending on if you're doing classification or regression. If you're doing classification, then you're predicting several like classes or categories. So let's say you're predicting what type of cat something is. Then maybe you might have one which represents how confident it is that it's cat A, how confident it is that it's cat B, how confident it is that it's cat C. So you have one output for every category or for every class. For regression, that's just where you're predicting a number. That's just however many numbers you want to predict. That's how many output ones you have. So if you're predicting one number, like let's say you're predicting the price of a house, you just have one output. And generally, this whole thing together is called a neural network or a multi-layer perceptron because it's multiple layers of perceptrons. And each of these like kind of vertical stacks that takes the previous input and then gets out another output of numbers is called a layer. And it's often called a linear layer. And it's going to be important when we're coding in Pytorch because Pytorch calls it a linear layer. Yeah, any questions about this part? I think it's review. And also activation functions, which go between the layers. And in Pytorch, you'll literally be putting them right after every hidden layer. So these are your 2 hidden layers, so you have 2 activation functions. You don't put them after the output, and you don't put them after the input, but after the hidden layers, you put the activation function. That's because the input layer is just the numbers that you're feeding into the neural network. So it's not really like a number you want an activation on. Like you might modify whatever your data set is. Like your input layer is just your data set. You don't want to like let's say ReLU in this case, it makes all negative numbers 0. Then that would mean suddenly all the negative numbers would be gone from your data set. And then the output layer is what you're going to be reading into your output, and you want that to be anything theoretical. So yeah, neural network, it consists of layers. And then after the hidden layers, there's activation, and then there's the output layer, and then that's how you get your output. Now, really the important part is how do we train this model? So the model makes a prediction, right? It takes in a bunch of numbers, it does a bunch of random multiplications, and it makes a prediction. So how do we make that prediction actually accurate? That is predicting something that's useful for us and actually correct. Well, how we do that is with data. And that's in 3 steps. Well, I guess, okay, step 0, I guess you could say, is make the model. So it's kind of assuming you have a model. Now, after the step 1 for training, like actually training the model, is you want to make a prediction. Or I'm just going to say predict. So this is, in other words, you're taking your model, you're passing in whatever inputs you have, and the model spits out an output. So you put in a picture of a cat, and it says, that's a cat, or it says that's a dog. It could be correct, it could be wrong. It just makes some sort of prediction. And at first, it's guessing randomly. In fact, so it probably is wrong. Now you want to see how wrong was your prediction. So that's step 2, which we call score, or I'm just going to call it loss. So loss represents how far away was what you predicted from what it's actually supposed to be. So if you predicted cat and it was cat, then that's perfect score, I guess. If you predicted cat and actually was dog, then the loss might be higher. So loss is higher if it does worse. You want to try to minimize loss. So step 3 is learn. And like I described, the model makes predictions entirely based on the weights, right? Entirely based on those weights that it's multiplying by. So what you can do is you can look at those weights and see how can I adjust them to make the loss lower. And you do that adjustment. You see, okay, if I might adjust my weights by like 1% this way and 1% this way, you can think of it like tuning a bunch of tiny little knobs and dials until the output is slightly closer to what it should be. And it gets, 1% closer. Usually you don't make a huge jump so that it matches it perfectly because you have a lot of different examples. You don't want it to learn off just one example. But you get it slightly closer. And then as you loop through this part, so this part is kind of all on a loop, happening over all thousands and thousands of pieces of data, and it's getting that tiny, tiny percentage point better. And over time, it eventually actually learns to make these predictions such that they will generally match whatever's in the data set. And if your data set's big enough, it will match stuff that's outside of the data set and stuff in the way, which is really why neural networks are powerful, right? Because they can make predictions on stuff that isn't in the data set. Any questions about the training loop? So prediction, score, improve. Then we move on to testing, which I put loop here, but it doesn't have to be a loop. You could just run testing once, which is now that you've tested that, it's learned the data set, you want to see that it. So what you do is you just get a bunch of data that it hasn't seen before. Basically, this would just, you'd section off part of your data set as being testing data, and you'd never show it to the model until testing. And then you give it to your model as a test just to see how well does it work on that test data. And usually it's just at the beginning, again, you split like 20% of your data into testing data, and then just test your model on that testing data to see how well does it work on data that it hasn't learned. And that's exactly the same. You just get the prediction and you score the prediction with loss. But this time, you don't improve the model with the testing data because the testing data is meant to be a test on stuff that it hasn't learned. Or simply on their training and testing data. The reason you also want to see about testing data is it prevents overfitting, which is basically where you memorize the data set. So if you notice that it's kind of working really well on training, but on testing, it's doing pretty poorly. That's because it's basically memorized the training data, but hasn't been able to generalize to real world data or testing data that it hasn't seen before. And that's called overfitting. And the way you prevent overfitting is, basically you just make the model. And then if you see that's overfitting, you kind of just try to make it harder for it to memorize the data. So you can add more data, but that's difficult. You usually are training on as much data as you have. The other options are you make it more difficult for the model to memorize the data by literally just making the model worse. So you make the model smaller, stupider. And often a simpler model will actually perform better than a more complicated model. Like for instance, for this one, you consider here, this is a very complicated model, right? It makes a lot of turns, bends, it goes up, down, and it perfectly fit the data, right? But then if I have some point if let's say this curve, it's just going to go here because it has no incentive to make anything special. If I put a point here, it actually does worse than the simple model. Because this model is very overfit. It tries to perfectly match every point rather than match the general trend. The other thing is you can train it for less time. So when you do your training loop here, the amount of times you loop is called your epochs. So if you just loop for less epochs, then it's less likely to overfit. Now, what's the statistic algorithm? How we update our weights? Right here for step 3, learn. We call that the optimizer, which is how it updates the weights. We would recommend you use the atom optimizer because it works pretty well and it's pretty simple to set up. The only thing you have to set is the learning rate, which is basically how much should it change its weights every step. So here in learn, it updates the model some amount. And learning rate is how much should I update the model? If it's very small, it will only update the model a small amount. If it's very big, it will change the model a lot every single iteration. In general, though, this is a very small number. I'd say it's like you should start off with like 0.001 and at most 0.1, maybe like 0.5 if you're like, I don't know, maybe there's some specific cases where it's like high, but it's definitely less than 1. So that's just updating. Yeah, so that was a quick recap of last week. I don't know if I think you guys were here last week. Were you here last week? Okay, so yeah, this is new for you, but that's fine. We'll come back. We'll clarify it as we go, I guess. Now, how do we actually implement all that stuff in code, right? The training loop, making the model, making the testing loop. It's a lot of stuff. I'd say honestly, if you kind of like get the idea of what you need to know there's a lot of resources online that will help you. But the way I recommend to do it is using PyTorch. There's a lot of like guides online that still use like TensorFlow or Keras or something. But nowadays that's like not really recommended or like standard. So the way I recommend is starting off by looking at PyTorch models. And so the first thing you want to do is make the model. So in PyTorch, to make a model, it's not too complicated. There is some like boilerplate, I guess you could say. I mean, it's not really. Which is that you first make a class. You don't really need to know what like classes are in Python to make one. You just first you define the class, which is like the blueprint for the model, and you just say class, and then whatever you want to call your model. So let's say I'm making a model for cats. I might call it cat model. I don't know, whatever you want to call it. Cat model, and parentheses, and then a colon. Right, that makes a class in Python. The only special thing is that you want to put inside of these parentheses, you want to put nn dot module. And I think you can import nn from Torch. So you can do torch.nn dot module if you're importing Torch. PyTorch. Yeah. By the way, the import for PyTorch is just import torch. Yeah, I'll put that up here too. Is this marker visible for you guys? No?
It's a little light.
It's a little light. I had an idea. I was going to do this earlier. Oh. Hmm. Yeah, that is pretty light. and then dot one. Yeah, but essentially if you put, actually now this is blocking this. But yeah, if you put nn dot module in the class, in the parentheses inside the class, that will basically tell it to tell PyTorch that this is a model that needs a bunch of other stuff being done on it in the background. And then this class will have two things inside of it, two functions. In Python, the way you define a function is to use the def keyword. In this case, you want to define a function with two underscores in it, and then two underscores, and then self as a parameter. So this is what's called a constructor in Python. This is just called automatically when you make the model. And you want to set up any stuff in here. Yeah. And then you have a second function called forward. So in init, you want to set up each of your layers. So if you remember, for a neural network, for a multi-layer perceptron, each of those was a linear layer. If you guys are doing images, each of those might be a convolutional layer because convolutional layers tend to be better for images. I think we talked about that. So in that case, you can do self. And the way you can initialize a layer, you can do self dot layer one, or whatever you want to call it. You can actually call it anything you want, but I'm going to call it layer one because it's my first layer. And then nn, because again, nn is whatever you imported. You imported nn from Torch, so it's the PyTorch object. nn dot n. Yeah, let's say 4 or 5. I don't know, whatever you want it to be. It could be any numbers. 4, 10. So there's the one. I'm seeing if I can adjust the video somehow to make it better visible. But basically, if you do self.layer1 equals nn.linear, that makes a linear layer, which you can pass through the values that which would basically represent, it would represent one of these. And one of these, what does it do? Well, it takes some numbers from the previous layer and then passes those numbers on to the next layer. So nn.linear represents one of these. In this case, we have 3 layers because again, our input is just the input numbers being inputted. So these 3 are the actual layers. But you can choose any number, and the model will basically figure it out. Let's say, yeah, and if I keep on going, maybe I would make layer 2, layer 3, and so on. The only other thing you have to do is the activation function, which, if you remember, it goes between the layers. And it's the same way, self dot, whatever you want to call it, activation, I guess, equals nn dot reload. And this one doesn't have any parameters. So linear has, oh wait, I forgot to mention, linear has 2 parameters, just the inputs and the outputs. So if we go back to this one has, let's say, 4 inputs, and I think it has like 5 outputs, right? Maybe this one has 5 inputs and it has 4 outputs. Or actually 5 outputs. The amount of perception, I guess, is the number of outputs. And this one has 5 inputs and it has 4 outputs. So depending on how many outputs you want, which I said the output layer needs to match and the input layer needs to match, but otherwise these ones you can choose however you want. And however many you want, you can have more layers, you can have less layers. Generally, if your problem is more complicated, you want more layers and more neurons. Um, but I mean, I'd have to talk to you about what your specific problem is, but like decide how complicated it is. And you put the activation function in between each layer. So now forward, what the forward function does is, and it has been called to basically make every layer. Forward is actually making the prediction. And that's pretty simple. The input variable here, you're given this input variable. And that basically is whatever you're inputting into the model. So whatever the model is getting. And it wants you to return an output. So in the case of take a layer, so let's say we have self.layer1, right? How do we take this input and pass it through the layer? So the same way, I should actually just go back to the slide. So take this input, like let's say there's 4 numbers here. I don't know, the temperature, the pressure, the humidity. Or let's say they're the pixels from the image on the cat, right? It's a bunch of numbers. We want to pass them through the perceptron layer. So it takes those numbers and it multiplies them and adds them together and does all that stuff. And outputs a new set of numbers. How do we get those new set of numbers from the original set of numbers in the code? In the code, it's pretty much just like this. You take self.layer1 and you put parentheses around it, and inside the parentheses, you put in whatever's going into the layer. So in this case, we're given that. That's just the input. And what this outputs, in other words, what we can set this equal to, is, I'm just going to call it partial. It's like partially through. Is a new set of numbers, which is after each of these perceptrons has done, multiplying each of the inputs, adding them together, multiplying each of the inputs, adding them together. It does all that calculation, and it's going to output a new set of numbers, which I'm going to call partial. I'm going to put it into the partial variable over here. Right here. Yeah. And then I pass it through the second layer, right? Because I want to keep going through these layers. After it goes to the first one, it goes to the second one, it goes to the third, right? However, there's something in between the layers, if you remember, which is the activation function, which just adds more complexity to these neural networks, makes them nonlinear, make sure they don't collapse. So in between the first layer and the second layer, you do want to put in self.activation, let's say, if that's what you called it. And you want to put in whatever you got out from the last layer. So this is what I got out from the last layer. So I'm just going to put it into the ReLU activation. And I'm going to output it back into the same variable, because in Python, you can just do that. So this will take in whatever that currently was outputted from the layer and then put it back. In other words, update the variable to be whatever was outputted from that activation function. And then you can keep repeating that with the next layer. Self.layer2, whatever, I guess partial. And then keep going with, you do a ReLU, then a layer, then a ReLU, then a layer. And then finally you get to the end. And what you do is I think I might have run out of space. But you basically just return, I guess, output or partial or whatever you call it. Once it passes through the last layer, you just return it. So you do return partial. Or in your case, you should probably change the variable name, but it might be called output or something. Can you actually see that? Ooh, fix them. Go. But yeah, it would pass it through layer 1, pass it through layer 2, pass through layer 1, pass through activation, pass through another layer, keep on passing it, and then it returns it. And for that, you just need the nn.linear and nn.ReLU. If you're using convolutions for images, you want to replace nn.linear with nn.conv2d. So that's what they're called, CONV 2D for convolution 2-dimensional, because your image is 2-dimensional. Yeah, so now we have forward, right? How do we actually calculate the loss and do the training loop? Right now. Well, you're figuring, okay. You want to initialize the loss, optimize our data, and model. This would be outside of your model once you're done making it. So like somewhere else in your code. You want to actually create an instance of this model, which is basically in Python. Um, in Python to like make an instance of this class, you just say like model equals whatever you called it. So in this case, I called it cat model, I guess. And then you can do like, and this will make this model class that you kind of defined here. So here, this you've like defined it. This is like the blueprint. And then here you actually make one of them, these cat models that you kind of specified here. You also need to make the loss function. So you're going to say like loss function, or I'm just going to call it loss fn for function, equals, this is the same. It's also, I think, nn dot. And then it depends on what kind of problem you're doing. If you're doing a regression problem, which is a problem where you're just choosing a number in a range, I would recommend MSE loss. Otherwise, I would make, if you're doing like a classification problem, I would recommend cross entropy loss. And these basically measure how correct was your model. So MSE loss stands for mean squared error. So mean means average, so it takes the average of the square of the error. And error just represents how far away the predicted was from the actual. So you predicted 10 and the actual was, I don't know, 15. You were 5 away, right? You predicted 8 and the actual was 7. You were 1 away. It takes that, it squares it, and then it calculates the mean or the average, because usually you're running this like several times. So mean squared error is a very simple one that's good for when you're predicting numbers. When you're predicting categories, like let's say the example I was predicting, is it a picture of a dog or a picture of a cat? You can't really subtract dog from cat, right? And you can't like square dog or cat. That's not like, doesn't make sense. So you have to use a different loss function, one called cross entropy loss, which will basically compare like each of your numbers, not as like a number, but as a probability that is that class. Because you're not really, your model's outputting like a probability. It's like 70% sure that it's cat and 30% that it's dog. It's not outputting like a number in a range, really. So you need a different loss for those. But again, those do the same things. They'll just calculate the predicted actual and give you back a score for how bad your model was. And you want to lower that number, obviously, because your models will be good. After you've initialized your lot, you can also initialize your optimizer. So your optimizer is what will be controlling your weights and like updating them every training loop to make sure they get better over time. So I'm going to call it optimizer equals, and I think this is actually like nn.optim.atom or something like that. It's not exactly like just nn.atom. It's like optim.atom or something like that. So that one you have to like create slightly differently. And then inside of these parentheses, you do have to pass in the learning rate, which again, if you want it to be bigger, it will make bigger changes to your model. If you want it to be smaller, it'll make smaller changes to your model. And you can just kind of play around with that number and see which number works the best. I would start off with learning rate equals 0.001. You also have to do pass in model.parameters. And you'll see this anywhere you Google, like how to make an optimizer in Pytorch. It will show you this. basically your optimizer is updating the model's parameters, right? So you need to give it the parameters because those are the things it's going to try to update. And then you need to initialize your data. We kind of covered that last week. You should have your data set ready, split into training and testing, inputs and outputs, so that you can input it into your model and compare the inputs and outputs. Right. So now the actual training loop. So the training loop is a loop. So in Python, the way you make a loop is you just say for I in range, and then however many numbers you want to loop through. And the amount of numbers is your epochs. So start off with with like, I don't know, 20 epochs is fine. That's like not too big, not too small. And this will loop for 20 times. And every loop the first step is, remember the 3 steps, they're predict, score, and then learn. So you want first to make a prediction of your model. So, okay, you could say prediction, or I'm just going to call it pred, equals, and you want to make a prediction from your model, right? So you just say model, and then in the parentheses, it makes a prediction from some inputs, right? So you say prediction equals model and then inputs. And where do you get these inputs from? From your data set. So if you're reading an image, this is where you'd be reading that image. If you're, have a CSV, this is where that output for the CSV would be. Whatever was in your data set, you're going to be inputting into the model here and getting a prediction out. From there, you need to score that prediction. So how good or bad was that prediction, right? And that will give you a loss. So you can say, okay, my loss is equal to a calculation between the prediction and the actual based on the loss function. So the loss function will calculate that for us, actually. So still didn't work. Okay. So now you compare the loss function, you compare the predicted values to the outputs. And what are the outputs? Those are the outputs in your data set. So you compare the outputs in your data set to what the model predicted. And you see how bad was that. And this will put that in the loss variable. So your loss will just be a number. Let's say your model did really well, maybe it'll be 0 over 0.1. Your model did really bad, maybe it'll be 100, maybe it'll be 1,000. But it really depends on the model and the loss function that you're using. After that, you want to learn. And to learn, I'm not going to write down these lines of code, but basically these are the 3 lines of code that will kind of do it for you. And Pytorch, this basically means it will optimizer.0 grad will reset the optimizer. Loss.backward will go backward through your loss and through every parameter and see how should I update this parameter, this weight, to make it better. And then optimizer.step will actually update the parameters to be better in your model, that tiny little bit. So that's the training loop. And if you do that, your model should improve. If you want to actually test it, it's exactly the same as this training loop, but you don't do the like optimizer.0 grad, loss.backwards, optimizer.step part. You can do with torch.no grad, which will tell Pytorch not to do background calculations. That's kind of optional. Yeah, okay. Now it's workshop time. So maybe if you guys weren't able to get a good view of this, it'd be nice to go around if you guys have questions about your model. That is it. Oh, I see. Yeah. So import torch is called torch, which is from your model. Yeah, I think it but lowercase t. Okay. Yeah, and I think the way you import nn is import torch.nn as a torch. Yeah, you can do torch. Basically, you can do torch and then there. And then yeah, and you see that will work. But if you want to like shorten it, you don't have to type the word and every time what people anytime is killed. Right, import torch stuff and then as and then. So now what that means is torch dot nn you same thing with the nn divide file, so you can replace torch dot nn with just nn. Or I still need to confirm that. Yeah. Files. Yeah. Okay, cool. Okay, so for that I would recommend image folder. Look up like torch data loader image folder. Image folder, yeah. Right. So what this will do is you give it some folder, and you'll see are there subfolders because every subfolder like a different class. Yeah. Yeah, okay. So you just need to give it this like base folder at the top. And it will automatically see that like, oh, this folder is for Obsidian and cats and folders. Yeah, true. And it will automatically group the images together based on what folder they're in. Okay. So it's really gonna be random. So see if you can get the image folder. Oh, you have a question. So we have. We're working with them? Yeah, we're working together. So yeah, we're and I ran it yesterday. We're using in consultation. Yeah, so we're using activities, and then basically I ran it yesterday, and it just takes like so long. Like I had it running the whole day yesterday, and it printed out in 5 minutes. Yeah, and like yeah. Well, one thing is you are missing the max pool layer. So there's convolution and that kind of. Wait, isn't this all I need? Is just the convolution method? Yeah, but what they typically do is max pool also, which reduces the image size, specifically for that reason, because otherwise it's like a shit ton of data. It takes too long. So if you Google like max pool, is that a layer? Yeah, you just add it in after con, or sometimes they add it after 2 convolutions. So it depends when you want to add it. You can add it after every single convolution, or you can add it after every 2 convolutions. But basically, if you do max pool of size 2 by 2, yeah, max pool 2D, yeah, 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 exactly. And then dot max pool 2D restart. I would do 2 stride equals 2. That's like the default. Like this is 2. And then the 2 stride equals 2. What that means is that I mean I kind of need to draw it, but basically like if you the convolution I remember it like passes over the image. Right? The max pool is it will take only the maximum value out of whatever. So in this case, if it's 2 by 2, it's on 4 pixels, right? Yeah. So max pool will take 1 out of every 4. And only take up the maximum out of every 4. Wait, so like in the image, like every 4 pixels, you choose the maximum. Yeah. So like reduce the width. How does it know what the max? Like the maximum value. So let's say they're in the pixel, one of the pixels is 7, one is -3, one is 0, and is 2. Then 7 is not that. And how is that not reduced with the accuracy? Well, theoretically, what your model knows. Well, your model will learn that it has to output a high value, and then only the high values will be kept. So it's basically being trained on the high values. So yeah, your model is being trained to only keep the high values. So it will learn to like kind of important things to put high values to important things. So is there like something like the high values are like more useful for the model time? Yeah, and that's exactly what you're trying to get the model to do is you're trying to compress the information, right? Yeah. So you want to train the model for that, like, oh, that's important things, it will weight them lower and they'll get discarded. More important things, it will weight them higher and they'll keep going through them. Yeah, but how would the model know like that the higher values that the more important? Yeah, well, that I think we don't know. Yeah. It's good. It's better easier with the graphic. So what's stride 2? So 2 by 2 means that it's the square that's taking the max from is 2 by 2, right?
Yeah.
Stride 2 means is that it's also moving 2 over. So theoretically, you can move 1 over. So here, it starts at this red box, starts at this red box, and it moves to this green box, right? If the stride was only 1, then it would move to this red box, and then it would move over only 1, so only here.
Oh,
And that basically wouldn't press the data that much. So you have to have 2 by 2 stride 2 so that it moves over 2 and only selects 1 from every 4. Otherwise, then it would be like selecting 2 from every 4.
And this is the new 2 by.
Yeah, exactly. And it would select 6.
So it's basically just like reducing the information from.
Yeah, but that's actually useful for the model because the model knows that not everything in the image is important. It's trying to summarize basically information from the image. So it actually wants to discard stuff, and this just gives it a way to do that. Yeah. In terms of how does it learn to actually like prioritize important things, like we don't know. Like we have these weights, and then eventually like the loss will go down if those weights are set to values that mark important things. But we just know that, okay, well, the loss decreases and it seems to be better, and those weights seem to be multiplying by important things. But we don't know directly. We just tell it, hey, do this and we'll do better. And it just keeps comparing actual and predicted. And eventually those weights settle on values. It's pretty important things. Are you interested in making a project?
Yeah, I was like, we're interested in creating okay.
Yeah, no, that's perfect. Just the first thing is try to see if you can find a data set. Oh, I should probably stop recording.